Imagine trying to predict tomorrow's market movements using not just yesterday's price, but the entire texture of how prices evolved over weeks. The researchers introduced Path Shadowing Monte-Carlo, a technique that generates synthetic market paths, so realistic they shadow actual history. Building on that vision, let's examine why predicting financial futures remains so difficult. Traditional models face a dilemma. They either oversimplify market dynamics or require massive amounts of data to train effectively. Meanwhile, the statistical properties that matter most, like volatility, clustering, and tail behavior, often get lost in the averaging. So how do the authors address these fundamental limitations? The key insight is elegant. Instead of trying to fit one model perfectly, they generate many possible futures using a maximum entropy approach based on scattering spectra, then cherry-pick the paths that best match the statistical fingerprint of recent history. Comparing approaches reveals the advantage. Where models like Heston or standard path-dependent volatility methods struggle to match the full statistical richness of markets, Path Shadowing Monte-Carlo maintains alignment across multiple timescales, while naturally adapting to recent conditions. This visualization makes the statistical alignment concrete. The scattering spectra capture 4 key statistical features across the observed S&P 500 data, a traditional path-dependent volatility model, and the new scattering spectra model. Notice how the SS model matches the complex structure of real market statistics far more faithfully than the PDV baseline, particularly in capturing the textured, multi-scale properties that traditional models smooth away. These theoretical advantages translate into measurable improvements. The results validate the approach across multiple dimensions. Volatility predictions improve noticeably, and the method generates more accurate option smiles that adapt to different market regimes. Perhaps most importantly, it achieves this without requiring the enormous datasets that typically fuel machine learning approaches. The authors acknowledge computational costs as a trade-off. Generating and scanning large path datasets demands resources, though this investment buys statistical fidelity. Future work might explore multivariate processes or develop smarter scanning algorithms to identify shadowing paths more efficiently. Path Shadowing Monte-Carlo shows us that sometimes the best predictions come not from finding the single perfect model, but from generating diverse possibilities and choosing the ones that echo the past most faithfully. Visit emergentmind.com to explore the full technical details and dive deeper into this elegant approach to financial forecasting.